So the top image is the data point. The image below is what it thinks all of the things are. And then the ontology, which again, super esoteric word that just means
Right.
a group of objects that it's trying to label. Um,
Uh-huh.
that's what it thinks everything is. So it labels the ground as that color. Like it labels the sky as that color. It labels people as that color. It labels the water as that color, and it labels sports as a different color. Hello.
Welcome to this week's episode of the Tangent Podcast, where we talk about whatever we want. No, but today we actually is our blue episode, so we will be a little bit more focused as far as that is concerned. And if you follow us on the Twitter or listen to any of the previous podcasts, specifically last week's episode, we told you what we were going to be talking about in our episode focusing on the enrichment of our mind, and that would be the idea of computer vision.
Yes.
Now,
Computer vision.
I will give a I will give a disclaimer, as we always do when it comes to this blue episode, is that most of the stuff that we talk about does not come from our own expertise. It just comes from the fact that we are two curious people who are very passionate about continuously learning, and examining our own lives. As what is it? Plato said, or Plato quoting
Yeah.
Socrates said that the unexamined life isn't worth living, and that's what we try to do. Is we try to examine our life constantly, consistently, in every aspect of it. So, with that disclaimer up there, is that this is just stuff that we have researched. We're going to do a little bit of a different format in the sense that Anthony here has done most of the research
Well,
for.
part of the reason is because while I don't have a PhD or anything like that, I do have a little bit of a minuscule amount of expertise in this topic. And so
Right.
I figured it would be easier for me
So
to, yeah,
I'm gonna play interviewer.
yeah,
That's actually, which fun fact is I do have some writing and journalistic experience. I would
yeah.
not use
So,
the term expertise.
right.
So I'm gonna be in my wheelhouse
Yeah.
as the journalistic inquiry mind,
Mm-hmm.
and you are going to be in your wheelhouse.
Yeah. Which is part of the reason why I figured, hey, we could try this out and see what
Yeah,
this works like because we're both in our own domains.
right.
Speaking of domains, I'm going to talk about the esoteric elephant in the room.
Ooh,
Um,
that was a good transition.
yeah. Any kind of science, computer science, biology, really any kind of specific technical domain has a lot of esoteric words. Even the word esoteric is kind of esoteric, which is funny enough. Words that are very specific and mean very specific things, and outside of that context could mean something completely different. Um, and the reasoning for that is, if two people within the same domain are trying to talk about something and communicate, it helps communication a lot. It does a lot for making sure that I can say something to someone else who's within the same domain and they understand what I'm talking about. And by domain, I mean like industry, skill set, whatever, um, topic of study. Um, and so the problem is that with some of these type of esoteric linguistics is when trying to communicate with people outside of that domain, it makes it very difficult, has the opposite effect. So today I'm going to try to not use those words, and when I do use those words, I'll give them a more connotative definition.
Hmm.
So anyone who's trying to follow, specifically viewers who don't know how uh, this domain works or have no knowledge of some of these topics, can follow along better because it's better for that kind of communication, and it's better to learn some of these topics if the words are not put in the very specific language, or the very specific language is not used.
All right. So that being said, let's get into it with the simplest, most basic, upfront question. What is computer vision?
Computers seeing things, as dumb as that answer is, that's what it is. So there are a lot of very interesting problems that people are trying to solve in the medical world and the astrophysical world. That meaning like astronomy and astrophysics, not like astrology. Just to put that out there. Self-driving cars, all sorts of different kind of things are very hard problems to solve. And that's what we want machine learning to be able to tackle. Or not even just machine learning, but different computer algorithms. We want computers to solve these problems for us. However, it is hard to get data. If I'm running a model on something, if I have just a list of information about a data point, so for example, let's say I have a helicopter, right? And I want my helicopter to fly itself and to maintain a certain height. Well, I can put in numbers of like, okay, this is the helicopter's velocity, this is what the wind speed is like, this is, how fast the rotors are turning, all this specific information, I can put these in as numbers. There's different ways of measuring that. That's I say it's an easy problem to solve, but it's not really that easy, all things considered. However, in terms of comparing that to computer vision problems, it's easy because the numbers are already there. I'm not taking an image and trying to discern things from this image because there's a lot of very nuanced things that you have to do when you just take an image or a video stream, because a video is just a bunch of images stacked on top of each other, that you have to learn from.
Okay. So how is this different than how computers quote unquote see things now? I mean, you're talking about inputting data, right? And we as humans, I know like we might have even used this analogy before on the podcast or maybe even in that season 0 or whatnot. Like our brains kind of operate similarly off of computers in the sense that we process information, but obviously we have a lot of different inputs. So how is it that computers process information now, and what would be the benefit of allowing them to process information visually?
Right. So that goes back to the same problem of like the helicopter, right? Instead of me having to put in all of the different information about what its speed is, how fast the rotors are spinning, et cetera, if I take a video of this helicopter or have a video on this helicopter, I should be able to glean information just from the video. So how fast it's going, what the rotor speed is like, just from looking at the actual pixels. And so there's different kinds of computer vision. There's also different kinds of models to help analyze that. There's things called, LSTM is the name of the neural network layer, and neural networks for now we can just assume are a black box. It's just a function. You have an input, you get an output, right? This specific kind of function takes multiple inputs, and so it takes a bunch of pictures stacked on top of each other, and so it can see motion, because it's hard to see motion from a single image, right? If I take a picture of the helicopter, or drone rather, for it's just like an actual helicopter, we'll just imagine a drone, right? If I take a picture of a drone, you can't tell how fast it's going. It's almost impossible to tell. There's very small details that would, if anything, there's no way to tell how fast it's going. What an LSTM, or a long-term, short-term memory, I believe is what it stands for. What it allows you to do is you look at 3 images of the helicopter and you compare, okay, in the first image, the second image, the third images, or however many. I said 3, but you can take as many as you want. What's the difference between these 2 images? And for example, if I was to show you a video of a helicopter, you would more accurately be able as a human to see how the helicopter or how the drone is moving, right? So that's one way. That's one way that you can use computers to have some sort of vision. But first, before you can do that, you need to know what even is a drone. How is a computer supposed to know that? And that's where the different kinds of object classification come in. And those, to put in the overarching terms, that's where you start to get object detection, semantic segmentation, and instant segmentation. And object detection is easy. there's an object in a picture, and you draw a bounding box around it. So you just have an image of a drone. You just draw a square around that drone, or the computer draws a square, learns how to draw a square around that drone, and says, "Hey, there's a drone in this image. I'm tracking it. I know what I'm doing. I know what I'm looking at." Semantic segmentation is a little bit different. All that literally means is you're taking each pixel and you're labeling each pixel. There's a word that people use called a class, a class list. All a class is just an object. Like, is it a drone? Is it a person? Is it a cat? Is it a dog? Though all of those are different types of classes. Class doesn't really mean anything specific other than like type of object. So I'll start referring to it as a list of types of objects. So it takes a pixel and it says this pixel belongs to a person, and it labels it. This pixel belongs to a drone, and it labels it. That's what semantic segmentation is. Instance segmentation is a little bit similar to semantic segmentation. It just labels individual types of classes. So my types of objects that are labeled in semantic segmentation, it just says, oh, this pixel belongs to Victor. This pixel belongs to Anthony. This pixel belongs to drone X. It labels specific kinds of people or specific kinds of dogs. Like, this is my dog, Gwen. This is your dog, Echo. That's what instance segmentation means. And putting all those together, you can start to build ideas of what is inside of an image.
Right. So, I mean, it sounds like, just out of kind of, especially when you're talking about the object detection issue of things, it sounds like a more practical, real world Google search, for lack of a better word. I mean, like, the ability to think of, like, I think, I don't know why this is the example that came into my head, but when someone is trying to identify, a criminal, and they stick that logbook, as you see on TV, because that's really my only experience with this. They stick that logbook of mugshots in front of a witness, and they have them individually flip through to see if any of those known criminals is someone that is the person that they saw. That takes forever. Now, it sounds like with computer vision, you're talking about having a camera or a computer do a similar thing, but probably at more astronomically rapid computing speeds than a human who can manually flip through a book of photos.
Yeah. I think it would be important to, and we can talk more about, like, the morality of using this kind of technology at the end. And so for now, I will change that metaphor a bit into something that's a little less gray area, and medical diagnosis, right?
Right.
That same idea can be applied there, because you take an X-ray, right? You take a picture of the inside of someone's body, and let's say that they have a what's the word? A mass.
An abscess. Mass.
Yes.
Yeah.
There's an abscess inside of this picture. With computer vision, the goal is to be able to take all of the information inside of this picture and say, is this cancer? Is this malignant? Is this benign? What is this abscess? And so that is one of the big problems that people are trying to use computer vision to solve.
I was going to say, just using that example, I would assume that the benefit then of that would be, instead of having a single medical professional or even a group of medical professionals within your hospital looking at the image of whatever this abscess is and diagnosing it, you could take the image, run it through a data bank of the compiled information of every medical, we're talking, theoretically, every medical professional, and have the computer then compare it to not just the observations and experiences of one individual who's trying to diagnose this, but multiple individuals.
Yeah. And while, just to clarify a bit, you're not really comparing it against a data bank or a database of other data points. That's what you use to train the model.
Mm-hmm.
Think of it as like a filter, right? You are training the filter on all of these different data points. So you basically, so this is, we can also talk about between supervised and unsupervised. What supervised means is when you're training the model, you give it labeled data. So a bunch of doctors, this is where you start to go have your data bank or your database of
Mm-hmm.
information. You have a doctor or a bunch of doctors or a bunch of grad students, really is probably what more likely what it is. You
Mm-hmm.
hand them a bunch of pictures with abscesses, and you say, "Hey, there's a cancer in this image. Circle, put a box around this, and label this as a cancer. Put a box around this and label it as just a benign abscess. Put a label around this and label it as a liver." And you basically do that for like hundreds of thousands of images, and you train the model on it. So then the model doesn't really, after it's done training, it doesn't have access to those data points anymore. It's
But it
just trained.
knows
Yeah,
it knows what a
yeah.
cancerous mass looks like. It knows what a malignant mass looks like
Yes.
because of the training. Right,
Yeah.
right. The
So it's
same
not
way
like,
the same way that a medical professional would just know
yeah.
because they went to school.
Yep.
Okay.
And so that would be what you're basically going to end up using when you hand it a new piece of information that the data set has never seen anymore, and it'll say, "Hey, this is what it is." And that's where you start to have like different ways of testing models to see if they're
Mm-hmm.
how well they're doing, how well they perform, and that's where you start to get like the accuracy measures. Is you have a training set, you have a testing set, and you already know how like what the testing set is labeled as, but the model doesn't, and so you just
Mm-hmm.
basically in the posterior say, okay, how well did the model do on the training set, or sorry, the testing set. So like, oh, the model
Mm-hmm.
predicted, 57 out of 100. It's really way more than that, but it will say 57% of the testing set. So the model has about a 50% accuracy. Obviously, you're shooting for way higher than that. That's just an arbitrary example that I pulled out of nowhere.
So aside from we're gonna stay away from the criminal thing, and
Yeah,
we're
yeah.
gonna we
We'll circle back
for
to
the
that.
time being, right? We'll circle back to it, and we mentioned the medical things. What are some of the other potential benefits? Like, why is computer vision and the potential of teaching computers to see
Mm-hmm.
the way that we see, because sight is a huge way that we process information.
Right.
Um, there's I reference Malcolm Gladwell all the time, but specifically I always talk about his book, Talking to Strangers.
Mm-hmm.
The first book by him I actually read. My sister Elise recommended to me, and I don't have the copy anymore. It's all filled with notes. It's a book called Blink, and what the book is about is that when you are put into a room, open your eyes and do a 360-degree spin and then leave the room, your eyes take in so much more information than you even realize that they do. It's just your brain acts as a filter to tell you what you saw, quote unquote,
Mm-hmm.
as only what was important. But if you can train your brain how to be faster in breaking down those visual inputs that you see. I mean, the average person, like when you enter a room and open, you basically see your eyes take in everything the light touches.
Yeah.
And you have the potential to process that information. So that's just one of the senses. And so if a computer had the ability to do that, what are some of the other benefits? What are other fields that make this concept super exciting in this specific space that we're
Right.
talking about?
So there is an obscene amount of information that is held within video and images, right?
Mm-hmm.
Just massive amounts. What's hard is for someone who, for a thing, an entity that doesn't know how to parse that information, how to take this glob, for lack of a better way of putting it, of information, and to like get meaningful bits of data out of it. Images are meaningless, right? And think about, especially in today's society, how many images we have, how many videos we have. There's so much data out there. that you can do stuff with. So if there is any kind of way to be able to parse information from all of this data, from all these globs of data, there's really no domain where this isn't useful. I think that would be an easier list to come up with like things where it's not useful because it's a much smaller number. Like you can think of anything really. So for example, banks, when if you've gone to a bank and you put the check in, you say, "Oh, I want to cash this check," to people who cash checks. You go to the bank, you go to the ATM, you put the thing in the machine, and the machine says, "Oh, this is how much money that the check says you're owed." That's done through computer vision. That's done through. I don't know if that's done through specifically neural networks, but it's done through a bounding box model, and then it compares your writing to probably some sort of model that knows, hey, this is what numbers look like, and then it makes a guess. And it's been trained on so many images that it gets very good at saying that your really shittily drawn number 2 is the number 2,
right,
in the check. Self-driving cars, another example. In astrophysics, labeling different stars, like what part of the star's life cycle is it at? The computer can be trained to know that. Really, any domain that you can think of, there's almost definitely an application of computer vision to it to make it.
So are there any realms in which computer vision is currently being utilized, like right now, or is it still so baby, or infantile, for lack of a more scientific term, in its development that the accuracy of it isn't up to par yet to be used in real world practical applications?
No, it is. So the check model, that's something that's definitely being used. As far as things that are actually being used in medical diagnosis, I'm not sure how far along it's gone. I'm sure they're using it to some extent, but there's almost definitely multiple humans that are involved in the process. It's more of a supplement. It's more of a let's see how well this works. An aid, if you will, in the medical industry. As far as I know, I don't think that it is, it's no robot doctor yet. The self-driving cars, I'm sure a lot of the lane watching, like the auto assist driving that's going on, I'm sure there's lots of computer vision that's being done in that. It's obviously not to the point where it's, again, solely relying on this thing. And it's just another supplement. As to other examples, I know that some satellite imaging is using it. And this is where you start to get into what I think is another interesting problem with computer vision is what data sets are you looking at? And so there's, like I mentioned before, there's something called supervised learning, which is, here's a bunch of pictures. Here's a video that we took. And actually, I can come up with a specific example. There's a data set called Coco Stuff. And there's a bunch of them. Or sorry, I'll use Cityscapes because Cityscapes is one that was used for YOLO V5, which, yes, that's an actual name of a computer vision model, of an object detection bounding box model, YOLO V5. And I'm pretty sure they trained the model on, let me see, is it Coco Stuff or was it Cityscapes? Oh, it was Coco Stuff. Okay. So Coco Stuff is just a very large data set with a bunch of different images in it. Actually, I have it saved to my computer because I was going to play around with stuff. And let me see how big Coco Stuff is. So currently on my computer, the Coco Stuff dataset, compressed, not uncompressed, takes up 38.6 gigabytes worth of data. That is a lot. To anyone
and you said that was compressed?
That was compressed, yeah.
Oh, jeez.
Let me see if I have Cityscapes uncompressed. Decompressed? Decompressed is probably the correct word. Datasets, yeah. I have Cityscapes decompressed on my computer. and it's chilling at a cool 118 gigabytes worth of data. Yeah, so pretty big, pretty big. And so what you have to do, I could look up how many images are actually in the data set, but it would take a while for my computer to calculate all that, and I don't feel like waiting for that at this point.
Mm-hmm.
But what someone had to do, or a bunch of people had to do, is go into each of those images in the 118 gigabytes worth of them.
Mm-hmm.
And mind you, a regular image, not that big, a couple megabytes at most. So that's a lot of images. They have to go through and label and say, this is a car, this is a human, this is another human. And so supervised learning has a huge bottleneck on actually going through and labeling data. Actually going through and having someone say, this is what this is, this is what this is, this is what this is, right? What is really interesting is unsupervised learning. And what unsupervised learning, it doesn't mean that you don't watch it. Just, oh, I'm gonna leave and let the model do whatever, and just whatever happens. All that unsupervised learning means is you hand it the data. So I don't hand it any kind of label. I don't tell, for example, for cityscapes, I don't say this is a car. I don't say this is a human. I just give it the data and see what it comes up with. And there's a paper that I was reading called Stego, Unsupervised Semantic Segmentation by Distilling Feature Correspondences. That is a mouthful. All it tries to do is take a bunch of pictures and label each pixel to a type of object without looking at any kind of ground truth. So any kind of answer, any kind of cheat that someone has labeled and given to it. And it actually performs very well. I can put some pictures of, and actually we'll link to the paper down below in the description of the YouTube video, in the description of the podcast episode, of
and in the show
sources.
notes.
Yeah, in the show notes of these sources, of some of these images, and it's really cool how well some of this stuff is labeled. I can actually send you a picture now, Victor, so you have an idea of what I am looking at. Let me do that. I just took a screenshot of my screen, but if you look, so the top image is the data point, and then the image below is what it thinks all of the things are, and then the ontology, which again, super esoteric word that just means
Right.
a group of objects that it's trying to label. That's what it thinks everything is. So it labels the ground as that color, like it labels the sky as that color, it labels people as that color, it labels the water as that color, and it labels sports as a different color. Which in this image, for those who obviously can't see it, it's just surfboards. It labels the surf. It's a bunch of people standing on the beach holding surfboards, and it does a really good job of it. The same for cityscapes. It labels a road. It's just a picture of someone driving a Lexus that's got like a dash cam, driving through a city. And so it labels the car in front of them. It labels the road. It labels the sidewalk. It labels the people. And it does all of this stuff when you've just given it the images. There is a ground truth in the data set. So there are different images that are labeled. They have different class identifiers, but that's just for comparing to see how well the model's doing. The model doesn't have any kind of access to that. And
that's interesting.
Yeah, it's really cool how well this is doing. And this paper published this paper 6 months ago, I believe. So this is like pretty new stuff. I was planning, I don't remember if I said this on the podcast or I was just talking about this to you before, but I was planning on taking this model and running it on my own computer and seeing what other kind of things I could run on it. So maybe taking a bunch of videos from YouTube and seeing how well it can label that. That was something that I wanted to do. I didn't quite get to that point because the model is not very portable. which means
Well, yeah, it's how many gigabytes was it compressed?
yeah, yeah, exactly. So yeah, it's just not something that's easy to run. I am gonna figure it out. I will, but whether or not I might make a YouTube video and post on the channel. I don't know.
Mhm. Who
If I
knows?
can come up with something good, I will.
Yeah. So what are some of the obstacles that are hindering this from further development? I mean, obviously the lack of portability
Yeah,
and the
yeah,
the amount of computing problem is it goes without saying. The computer processing power necessary
yeah,
to run things like this, programs like this, to even have them do anything useful has to be astronomical, just with my basic understanding of hard drives, gigabytes, terabytes, and computers and how that goes. So, what
yeah.
are some of the other obstacles that are kind of hindering this computer vision field?
Right. So let's imagine you're Joe Schmo. You're me. You're a Joe Schmo who's trying to run this model and train a model from scratch on your own computer. What does someone
Hmm.
like that need? Well, you need a really good GPU, if not multiple GPUs, right? GPUs are the core and the heart of how these models get trained, just because computer graphics, even if it wasn't image or computer vision, even any kind of machine learning, the heart and soul of training any kind of machine learning is a GPU, because the same kind of math that's done in a GPU is the same kind of math that machine learning models need to train well and to train quickly. Um, what's something else you need? Time. You need lots of time. Some of these models have been trained for weeks, like straight, just training the model straight for a week. Um, and that's how they start to get so good, because you do lots of iterations, you do lots of different sample sets, etc. The other thing you need, like I've mentioned, is you need labeled data thus far. That's why Stego is so groundbreaking if this is the kind of quality you can produce out of anything, because unsupervised learning is super important. It drastically reduces the amount of human input in dataset design, which in that, when I say that, I mean actually saying like, oh, all I would have to do is say this color are humans, this color of this object are sports, this
Hmm.
the color of this object is roads. I don't have to do that for every single picture. I only have to do that for what, the cityscapes only has 6 different objects that I have to label,
Hmm.
so drastically reduces that bottleneck, because that's a huge bottleneck.
Hmm. Hmm.
Um, Also, having access to some of these data sets, a lot of the tech companies make money off of producing data sets. So being able to say, hey, I have this data set that I've collected from all of my different users on my social media platform. By the way, yes, that is one of the things that lots of social media platforms do when they collect your data, is they run all of that data through these kinds of models. And so when you accept the terms of service, you are accepting that. Um, and social media platforms make money off of that. So be aware. That's another roadblock for some people who want to just try to do this stuff. And then,
Right.
there is a lot of mathematics behind this. A lot of this is just pure math. And so that is the bottleneck, is knowing what is the new formula, what is the new mathematical function that I can do to these images to get better results.
Hmm. So, how many years out? Like this when you first told me that you wanted to talk about computer vision,
Yeah.
I I was like, I have no idea what that is. I have to Google it to
Yeah.
to figure out what you're talking about. Um, so my question is that you being somewhat of a student in this realm, and this might just be something that's pure conjecture, pure your opinion, but like
Mhm.
the the ever progression of progress, trudging forward. How relatively new is this concept for it to be as far as it is, and how far out do you think we are to seeing things like computers visually identifying and getting over some of these obstacles that are in their way, just being part of like something that's daily in use, either by tech professionals, medical professionals, business professionals, and stuff like that, to it being something that still needs a lot of oversight and refinement, it seems.
So a lot of uh, like the concept itself, not new at all. I
Right.
would wager a guess that this concept has been around for a very long time, almost as long as, if not longer, than photographs have existed, or at least
Mm-hmm.
film has existed.
Mm-hmm.
Um, Somewhere between the conceptualization of computers and film slash photography, I'm sure this idea has existed. In terms of like the actual innovations that have made it possible, if I was to take a guess, I'd say relatively new. I would say that there were probably major strides made in like the 80s and 90s. Even more major strides made in the past 10 years or so. So to think of like the progression of exponential growth, it was probably like a big jump in the 80s and 90s, a big jump in the early 2000s, and then an even bigger jump in the early 2010s, and then maybe an even bigger jump in the late teens, like 20 teens, like 2016, 2017.
Mm-hmm.
And now you have this paper that just came out for Stego the past 6 months. And I think that if Stego can be capitalized on, that is a huge improvement. That is a huge, a massive leap for the field of computer vision.
Mm-hmm.
There are also other types of models that can be run, because just identifying objects is good, really good. But there are still things you have to do with once the objects are classified. Um, so, for example, even if I can classify a tumor, what do I do now? Right now, what? And so I don't think you're going to get to those levels of good um, for a while, because you still have to run other types of models on this model itself. So, for example, let's say I want to come up with a diagnosis for a tumor. You first need to run the image, the X-ray. You need to run that through this model. But then you need another different kind of model, which is probably would be some sort of reinforcement learning model, some other kind of neural network that's been trained on what to do with tumors and different kind of treatment options. You would need to run the data that you've gleaned from the computer vision model on that model. And how many of those are trained already, I don't know. So that becomes another roadblock.
Mm-hmm.
But in terms of like being able to use just the object identification, I would say maybe like 5 years, we might be able to use it and rely on it pretty well if we keep maintaining this same kind of growth. Um, from things like Stego, there's another one called Dino, I believe. From its emerging properties in self-supervised visual transformers. That's what there's a Dino paper. I can link that back in the description.
Mm-hmm.
But the growth is exponential for sure, and it's pretty quick, which is it's breathtaking in a good way and a bad way. But just because it's breathtaking in a bad way, don't forget that there's a good thing about it. There's a good part to this.
So let's talk morality a little bit.
Yeah.
Because I'm just thinking in because let's criminology and law enforcement aside,
Yeah.
right? Cause you mentioned the thing about self-driving cars, and there's always that, there's that internet adage. I don't know whether or not this was actually a case, but I know that I've seen lots of hypotheticals where it was discussed and people arguing for what size. You have a self-driving vehicle that gets into an accident.
Mm-hmm.
Who's responsible? The person riding in the car, the computer driving the car, or the software company that developed and wrote the algorithm, for lack of a better word, that's running the computer vision that obviously failed, that made that car
Right.
hit someone else or hit something else.
Well,
Like who?
first
How do
off,
you hold a computer responsible?
right. Well, first off, you're lagging, so I don't know if your computer isn't plugged in or something, but you are.
It is plugged in.
Oh, okay, because you were behind a bit. You cut out, but I got most of that.
Yeah.
The other part of it
We got a
is
storm coming in here.
got it. The other part of that is it might not be the computer's fault, and more than likely, it's not the computer's fault. It's the human in the car. If it's two self-driving cars that collide, okay, yeah, then it's more than likely the computer's fault. But if it's like a computer in a self-driving car colliding with a person who's just driving a car, it's more than likely not the computer's fault. It could be. I'm not. Don't get me wrong. It totally could be. But human drivers are more apt to making bad decisions quickly than the computer is. And part of the morality behind it is what can we benefit from, and this is a very subjective take, and I'm admitting that. You have to obviously quantify what does benefit mean, and it means like, and when I say benefit in this term, in this context, I'll define it as being ecologically important or ecologically beneficial. So it makes our world better in terms of our environment and protecting our environment. It makes humans in general have better access to the things that they need. That's another thing that I mean when I say benefit humans. And it also means that humans are safer. It means that humans can be safer. Or not even safer, but like have less chance of things going wrong. I'll put it in that context. And so one of the things that I'm pretty sure it was either Tesla or Elon Musk were talking about is self-driving trucks. So trucks along the highway that are driving themselves. And one of the really cool things that you can do with that is there's this thing called drag. To talk a little bit about physics, there's this thing called drag. And when you have a very large load in a truck, trucks are big, they create lots of drag. And what does drag do? Drag makes you have to use more fuel and to do more work to push this vehicle. That's just how aerodynamics work, right? Now, there's a funny little thing with large trucks that if you've ever watched Mythbusters, there's a really cool episode of Mythbusters where they test this, where tailgating, and again, I don't recommend that you do this at all. This is really bad. This is really stupid. However, if you were, say, driving along the highway in a car and there is a big truck in front of you, if you were to get really close to the back of the truck and just stay there, you would be using way less fuel because there's a pocket of low air density behind the truck. And so if you stay there, you're going to be doing less work pushing your car. Because you're doing less work pushing your car, you use less gas. Now, if you have self-driving trucks, you can do that. You can have two self-driving trucks safely daisy chained behind each other, and so their fuel mileage just plummets. Their fuel usage, their fuel mileage would
fuel consumption, right?
Yeah. And so that's better for it costs less to transport stuff, which means that people have better access to food, to clothing, to whatever the hell they order on Amazon. We can pretend that it's a necessity. It's definitely not, but we can pretend that it's something that's necessary for their survival. It means that they use less diesel. Using less diesel, it means that there's less of an ecological impact on the environment. And there's other things that you can glean from this, and you can extrapolate from just this one example. That could make these kind of advancements good. There are definitely, to go towards the criminology example, there are ways that this can go poorly very quickly, especially when it's used for things that are criminal or in the domain of criminology, because humans are fallible, and there are
Hmm.
reasons, like, humans are fallible because there's a lot of data that points towards certain biases, and biases do exist in machine learning. That is a thing. There's a thing called bias that exists in machine learning, and any kind of artificial intelligence. So just completely relying on certain models wholeheartedly, you have to make sure that you're discounting this bias, because that's when you start to see like emergent properties that humans have in the AI that are not necessarily beneficial. For
Hmm.
example, racism. You might see maybe
Right.
an emergent property of racism in the model, which is just not great. And a lot of those domains are, you need to make sure that we are not completely relying on them. You can also go even deeper into the subject of morality with machine learning and computer vision, of like, well, what does it mean to be human? And if we're just relying on these machines, like, you could go to the Wall-E principle, where it's like, okay, well, maybe
Right.
humans do need to do something in order to, what is the meaning of life? And yeah, you can make those sorts of arguments. I'm not well prepared to make those arguments currently, for or against. So anything that I say is super
Off the
subjective,
cuff.
off the cuff,
Yeah.
um, just straight
Hmm.
ideas that I can think of. Um,
Right.
but yeah, those things do have to be considered, especially as we progress.
Yeah.
And if
Right.
as we progress faster, they need to be more well thought out. And even if you go to try to like
Hmm.
download NVIDIA's CUDA toolkit, which is a
Hmm.
toolkit for running machine learning models on your GPU, they have like morality
Hmm.
agreements where you have to say like, I plan to use this in an ethical way. And I don't think that that's like the terms of service. You can just click through the terms of service and say, yeah, sure, whatever. It is still legally binding. However, you can still click through and say, yeah, sure, whatever, and get away with some stuff. I don't think it's a cure-all fix, and
Right.
I don't think it's anywhere near that. But at least it's progress in the fact that you have to start being more ethical, and have more thought behind using this model. So it's not just like the Wild West, you know, we don't give a shit what's going on, guns blazing. There are definitely people who are talking about these issues and are thinking about these issues of like the morality of using these models once they get to the point of being really good, because there is a point where they will get really good.
I made it. So I made it this far. You should be proud of me without a single Skynet joke.
I was waiting for it.
But
I
am I still
heard
lagging?
you a little
Yeah.
bit. Yeah.
No, no, no. And listen, yeah, there's this whole thing about, that I don't know if it's made so much anymore, but my generation and the generation definitely before me was like, don't make the computers too smart. And listen, from what I can tell, the majority, at least where we are technologically, the majority of the moral implications that could be sketchy in this realm of computer vision have 100% to do with human error,
Yeah.
right? Because a computer, let's just talk about racism for a second. A
Mm-hmm.
computer can't learn to be, isn't just racist. It has to be taught through, you know, through its application or through the subsets that it's told to filter things
Yeah.
that.
You mean it goes through
Um,
what is included in the data that it's learned. Like the data set that it
right,
learns from.
exactly. It's the data, right.
Yeah.
The data input teaches it that way.
Yeah.
Uh, the only thing that I was thinking about as far as moral implications for things like this, let's move away from that and just talk about the medical things, because medical the ability to run something through, uh, let's talk about real science fictiony but future science stuff, you
Yeah.
know take a picture of the inside of someone's body, run it through a diagnostic machine,
Mm-hmm.
and have it just spit out all the things that are wrong with it. The there's always that possibility of a malpractice. and of a diagnosis,
Mm-hmm.
but the machine says that it doesn't. And then they go about their life and then they die. That's where malpractice suits like live and breathe. And then who do you blame? Do you
Right.
blame the medical facility that used the machine? Do you blame the person who coded and basically gave the information, the data to base its conclusions from? Do you blame the machine itself? But the thing that I'm thinking about in regards to that is, like, right now you mentioned, and it was an arbitrary number, I'm sure, the idea of 50% accuracy,
Yeah.
right? Obviously, if something's given away, uh, doing a diagnosis that's 50% accurate, you're always going to need that human touch, that human double checking.
Mm-hmm.
But the fact of the matter is, if a computer through this computer vision visual input learning were to get to a place where it would be 90%, and I'm being generous, I kind of think 85%, where it was 85 to 90% accurate, I would argue that that is still more accurate than a human diagnosis.
Mm-hmm. Well, let me give you some numbers because I do have some
Okay.
numbers. Um, this is not having anything to do with the diagnostic per se. This is from
Mm-hmm.
the paper,
Right.
the Stego paper. So this is like accuracy in correctly labeling what is actually in the image. It doesn't say
Right.
like, and this is just the on the data sets that it was trained on. So this is Cocoa Stuff, this is Cityscapes, and this is Potsdam. And so if you look at the picture that I sent you, it gives you an idea of like what is
Right.
in the image. So like Cocoa Stuff is just a bunch of random things that it's given. For example, the
Mm-hmm.
people at the beach going surfing. Potsdam is a lot of aerial view, like terrain, how to label different kinds of terrain from the sky from satellite pictures. And then Cityscapes is just a car driving through a city, taking pictures of. Really, it's a video, but taking pictures of
Mm-hmm.
the things around it. And so,
Mm-hmm.
on these three data sets, the accuracy from Stego was 56 using unsupervised clustering, which, put very simply, is given the data, just guess at what it is, at what the answer is. And then linear probe style metric,
56%.
56%, 56.9 if we're being precise. And then there's
Okay.
another measurement because accuracy is in everything, but it's harder to describe. It's mean something over union. I forget what the I say. It's MIOU. But it's a harder to describe metric, so I'm not gonna go too far into it. Um, but that's 28.2 to people who know what that means. The linear probing was 76.1% accuracy, and the mean, I think it's mean iteration over union, was 41. And to put that into context with other models, you have ResNet, which was in 2016, has an unsupervised accuracy of 24. And just for simplicity, I'm just going to go over the unsupervised accuracy. So it's only a small part of the picture in terms of how good these models are, but it does paint the beginning of the picture. And so you have the top of the list, which is ResNet, 2016, 24% accuracy. Dino or Dino in 2021, 30.5% accuracy. SIFT in 1999, 20.2% accuracy. PICIE, PICE is what it's sometimes called, in 2021 is 48.1% accuracy. So over time, we are getting better, and
Mm-hmm.
Stego is currently at 56.9 for unsupervised accuracy, which is like okay, like right. And if you look at how this growth goes from 1999 to now, it bounces around 20 for a bit, and now it's shot up to 56. For the linear probe, it's a lot different. The linear probe bounces around 40s for a bit and then jumps up to 76. So the accuracy is getting better. It is progressing. To just put some real numbers behind my hand wavy 50% that I pulled out of nowhere.
Right. No. Real numbers are always good.
It's those
I
unreal
think.
numbers that are an issue.
Mm-hmm.
It's a math joke.
Math
Um,
joke. No, these are. This is just an interesting concept for me because I mean it's that whole going back to the morality thing. It's the whole thing. Like, do you hold the tool responsible or the person or how the tool is used
mhm,
responsibly for something? I've said multiple times in the realm in which we talk a lot, martial arts and self-defense and stuff, because that's where we both have an intersection of our experience. Like, a hammer can be used to build a house. Hammer can also be used to commit a crime,
mhm,
right? So that doesn't mean that you don't develop and make a better hammer.
right.
It means that you have to, as what it sounds like is being um thought of, you have to think about these things. And I liked what you said, the what are the benefits versus what are the risks? Like, those are the things that need to be weighed. So if
Right.
we're talking about that, the accuracy, let's use this 56%, go
Mhm,
back to the malpractice thing. If it's 56%, the risks still outweigh the benefits. So hold off on using it in that field. But if you get to the point where the accuracy of it is 90% higher or higher,
right.
right? Well, now all of a sudden, faster diagnosis, so maybe you can catch things sooner.
Mhm,
Now it might be worth the risk of a misdiagnosis because the benefit of catching something medically sooner is so astronomically better. So that's everything is a tool,
mhm,
and I have these conversations with people all the time in regards to technology, the internet. If you were born in the late 80s, early 90s, like we were, we remember both worlds, right? We remember a world without the internet, and we remember a world where everyone can carry the internet in their pocket. I heard a comedian once said, like, you work at Walmart, why do you need unfettered access to all of this information at your fingertips, right?
mhm,
But it's just the nature of the world that we live in. And I just think it's interesting that people are so quick to blame the unfettered access, blame the technological advance,
mhm,
as opposed to say, well, no, this is the world we live in.
right.
Uh,
And to take more
so
responsibility
instead,
for.
why don't we teach more responsibility?
Right.
Not to get into another conversation like we did last week about two dudes who don't have children talking about parenting,
Mhm,
but I've got a couple friends, a couple different friends sets
mhm,
of parents, and they're all over the map. Like, this set of parents are like, well, we don't let our children watch TV until they're at least 8 because it's, you know, it's unresponsible, and we want them to not be stunted in their imaginative mental capacity. And then you have this set of parents over here that's like, I've got 4 kids, they're all within 2 years of each other, I just need 30 minutes of rest time, and the easiest thing to do so that I can make dinner
right.
is to put them all in front of a hour TV show so that I can cook for the family.
Right.
Who's right? No
Yeah.
one. Who's wrong? No one. It has to do with the utilization of technology. Can you utilize technology in a way that stunts your child's mental imagination? 100%. Can you avoid technology? Speaking to the homeschool community, which I am also a part of,
Mhm,
or was a part of. Where you stunt your children's growth and mental capacity for development? 100%.
mhm,
I think I think I like the the questions and the thoughts that topics like this bring up, in the sense of you can't stop the ever forward march of technological advancement.
mhm.
So you have to have these morally responsible conversations about what these things mean and balance everything. Everything is balanced.
Right.
This has these great potentials.
Yeah. It
This
has to do
has
with
this
your
great
agency,
harm.
I'd say. I would say it comes down to like
I love that word.
what is my agency in this matter? Can I stop technological advancement? Can I personally
Right.
say to myself in isolation, there is no technology, there is no technology, there is no technology, and just pretend like nothing exists? Yeah, I guess you could try, but you don't really have any agency in that. You don't have the option to say like, oh yeah, this stuff doesn't exist. So what can I do about it? I can make choices that use this technology responsibly and put forth arguments to other people about, hey, maybe we should try to use this kind of stuff responsibly because it's going to happen anyway, right? But just because it's going to happen anyway doesn't mean you don't have any kind of choice, right? You're almost always going to be given a choice and have agency to some degree because that's kind of what humans are about. Like you can make the argument of free will, whatever, but there is agency. You do have a choice to some extent, and so I think to end, because we're over time, um, to end that is what I think we can take out of this is there's a lot of very promising things being taken out of this field, out of this domain. The choice is how do you want to use them, and I leave that as an open question to
Yeah.
the listener. And also, hey, there's lots of resources if you want to learn more. If you want to actually delve more into this field and get into the nitty gritty, go for it. It's a lot of fun. It's a lot of, as someone who has had lots of pain and suffering trying to make some of this stuff work, it still is a lot of fun to get to the end of the day and to get the result that you want to see. To see, oh, this is like a labeled picture that came out of nowhere. It can be worth the struggle. And so if you think that you're interested in that sort of thing, go for it. Tons of information out there. Lots of
if you
good YouTube videos, papers, lots of stuff.
Right. And if you have kind of a, we talk about body, mind, and spirit here on the Tangent Podcast a lot, and the blue episodes are generally where we delve into the intellectual mind part. And if you have a topic of conversation that you think it would be interesting for us to delve into a little bit and discuss, you can tweet at us, you can direct message us on Instagram.
Comment in the
we'd
YouTube
love
video.
to
I don't know how you can
comment on the
these
YouTube
podcast episodes, but sure, if there's a way.
Sure. Yeah. The point is that we just want to take our same love for learning and discovery of new things, and we want to share that with people. We want to share it with you, and if you have stuff that you're excited about, I want to hear about it personally.
Yeah.
Think it would be good.
That'd be cool.
All right. I think that's it, and then we can talk a little bit about our spirit next. Right? We're on body. We're on body. Our tri-weekly body check-in next week.
And it's the first episode where we're gonna have goals that we set for ourselves that we have to return to.
Oh yeah, that we can update on those goals.
But yeah, that's gonna be it for us.